Okay, this week we're going to talk about the weather systems where we live. What we're doing is slowly working on, we learned each one of the variables that go into making these weather. And now we're talking about planetary scale. Now we're going to come down to our scale of our area. And the next we're going to move into smaller scales, such as thunderstorms. So let's just look at our weather systems this week. What influences the weather in the mid latitude? So with that, first thing you got to know about is these large air masses. We've talked about them at different times. We've talked about how high pressure can cause them to develop, how the contrast between one air mass and another creates a front. Well, there are source reasons for air masses. You think about it, the air mass develops because high pressure sits there for a while and allows the air to take on the characteristics of the underlying ground that it's on. Well, in the United States, it's fairly hot and dry to our southwest in the U.S., almost a desert climate. So we have the continental tropical air masses there, which is basically a hot, dry air mass. You go up to Canada, you get the polar, and you go up in the Arctic, you get your Arctic air masses. There are maritime polar, which form out over the open oceans and the northern oceans, and the southern oceans and form a maritime tropical, which is very warm, humid air mass. Where these air masses come together is where you get the bad weather. So here are some of the properties that basically exchange heat and moisture with the surface, cooling, adiabatic heating, all of that causes air mass to modify with time. And in the wintertime, for example, you get continental polar or even Arctic Arctic air masses coming down from Canada. And when they come into the United States, if there's snow cover, they maintain themselves. They do pretty good at keeping very cold. But many times, I don't have snow cover over on the east side of the Appalachians. So what happens is you get the air coming across the Appalachians that is bitter cold back in Ohio. It begins to warm. It warms because we have the bare ground over here. It begins to destabilize, triggering convective currents, and it gradually gets a little bit warmer with time. So the air masses are modifying. Now, maritime tropical don't modify quite as fast because they gradually lose their moisture. That's one of the key things that's happening here. So here is just an example of a stationary front where two air masses are next to each other, but they're not moving either way. But some of that warm air is being lifted up over that stationary front at the higher levels. Remember, everything's three-dimensional, so you've got somewhat of a southerly flow at the upper levels here, maybe pushing some of the warmer air up over that cold dome of air. Well, as it rises, it cools. We've learned that. As it cools, it forms clouds. So the most cooling and the most clouds are very close to the warm and humid air mass, with less the further up you get. So a lot of times if you see cirrus clouds or thick cirrus getting thicker with time, it's some kind of warm front moving towards your area. And here you have that situation where the warm air comes towards you, and you have maybe snow even falling out at the very far north, and it gradually changes to freezing rain or rain as the warm air gradually approaches and modifies the air fast more and more. Cold air is denser, so it's going to displace the warm air very quickly. So when it does that, it means it pushes the air up faster. So you get more intense precipitation. Sometimes you get thunderstorms, maybe heavier showers. And here is just depictions of different directions cold fronts can come down in the eastern U.S. This is a typical backdoor cold front, one I kind of hate in the East Coast, because what it does, it brings, you notice the high is always going to be to the north, and it always pulling the air in off the Atlantic Ocean. So what you do is you get a maritime polar air mass a lot of times. Sometimes you get some continental polar, and it brings in moisture at the low levels off the ocean and gives you clouds. Makes for a dreary day. Occluded fronts, what are they? Well, occluded front is where a cold front basically catches up to and pushes a warm front out of the way. A warm front's pushing into cooler air. Well, This cold front's coming from the west and is just lifting up that whole warm air mass, pushing it aloft. And it forms an occluded front where it's cool or cold to the ahead of it, and it's cool or cold to behind it. Now, if the air mass is colder behind it, that's a cold occlusion. If the air mass is colder in front of it, that's a warm occlusion. And here you can see the example of that. The Norwegian cyclone model has been around for years, and it really is the best model for looking at conceptual view of how these extratropical cyclones we're going to talk about form. So the extratropical cyclone forms because you have cold air and warm air apart, close to each other, the contrast in air masses. You have a jet developing aloft, which allows divergence to begin. Divergence begins aloft, and you begin to get low pressure along these frontal boundaries. So you develop a warm front out ahead of it, the cold front behind it. As that surge of cold air pushes south, more of a meridional flow pattern, you begin to low even more. And the clouds start looking a little bit like a comma, don't they? And with time, they actually do form a comma head. And eventually, you can see here there's a large occlusion. What happened here is that this cold front overtook this warm front and formed an occluded front. Now, where this new warm front is, down here, many times new low pressure may develop there and move up. This is extratropical low pressures, which is the same as any kind of low. And here you see the pattern you're going through with it. The pressure deepens with time, begin to form an occlusion at the bench back at the end. Here is another way of looking at it. So we wanted to look at air masses and how they flow around an extratropical cyclone. So you have a warm conveyor belt that brings up the warm, moist air into it. You have a cold conveyor belt that kind of comes off the north, northeast, across it. Notice how that flows back here with time. That cold conveyor belt is what actually creates the comma head and causes the lift back in the backside. And you have the dry, cold air coming down behind it. Dry air sinks behind this low also. And that sinking motion can cause a dry slot, which may end the precipitation early. So this is all looking at different ways of looking at the same thing we just looked at in the Norwegian cyclone model. And here you can see the different sectors of a low, different kind of precipitation. One of the key ways of looking at where the low is going to move is just seeing how the pressures are falling. Where the faster pressure falls, typically that's where the low is going to be moving to. Here's the different kinds of lows, principal cyclone tracks. One of the key things about these lows is the closer they are to the moisture, the more moisture you get. So the Alberta cyclones are well up north. They're fast moving, very cold systems. They don't have a lot of moisture to tap, maybe the Great Lakes, but that's not a great moisture source. Whereas a Colorado low will have the moisture from maybe the Gulf of Mexico coming up into it, so it would have more moisture to work with. And depending on which side of these lows, especially in the wintertime, you may get a whole different variety of precipitation. If you're on the west side and you stay on the west side, you may get all snow, very heavy snow, maybe even a little bit of ice closer to the fronts. But then on the south of the thing, the lows, along the cold front, you probably get some thunderstorms, maybe even some severe weather. And you get rain out ahead of the warm front. Maybe it starts as snow, but it probably changes over to rain. So it all depends on where this low goes. Another thing about extratropical cyclones is they get colder aloft. They're very intense aloft, so that they actually become stronger and colder with height. Now, if you have a weaker one, they still do it, but they slope more. Warm core is more of a thermal low, it's more stationary. It has no fronts associated with it, and it tends to form over very hot, humid, hot, dry areas. And because, remember, warm air is less dense than cold air, so the pressure doesn't drop as fast in the vertical. It actually forms anticyclones aloft. So it weakens with height. So And here are just some other breezes that you get in our mid-latitudes, called the sea breeze and the land breeze. They impact particularly along Lake Erie, maybe, or over the oceans. And mountain and valley breezes in West Virginia. You get these all the time, where they warm up the slopes or whatever and cause the air to rise and sink in the middle of the valley during the summertime. The heat, hot of the day, and at night, cold air drainage comes down, causes the air to rise in the middle of the valley. And this is actually something that firefighters use all the time when they're fighting forest fires. So I just wanted to show you one quick thing here. This is currently where we get it back here. Well, it's going to take a minute to come back. But what I wanted to show you is where the fronts were at this time. And these fronts, notice there's not many fronts. There's one moving through the eastern United States, pretty strong low up here, 985. Pretty cold air coming in, too. Starting to feel like fall, even turning towards winter. And there's big high pressure over the Midwest. Well, you look at that big high pressure, you'd say, well, okay, it's going to be sunny out there, right? Well, it's not. We'll just leave it at that. It's going to come back here in a second and show you that. But there's a lot of clouds, even some clouds moving up in towards West Virginia with this and all. And you can see like a low. And you saw a low that was well down here. But this is actually spread all the way up further north. And with that, when you look at it, what it is warm advection. You can find it here at 850 coming north. So that warm advection coupled with right rear quadrant of a jet streak has divergence aloft. So there's divergence, and the warm advection are triggering rain showers, even some snow showers out in the Midwest right now, and moving towards the east. So hope you got a little bit of an idea where your weather comes from in the mid-latitudes now. Let me know if you have any questions.